And so if you're increasing, then it is 100% of what you have, plus if it's interest, 5%. So I know that I can convert these both into a decimal. 100% is 1, and 5% is what, 0.05. So my multiplier is 105. Okay. If something is decreasing, and when we're doing it exponentially, it may be decreasing by 5%.
Right.
Okay?
So like on the.
So if it's decreasing by 5%, we have 100, we're starting with 100%, and it is a decrease of 5%. So what is the multiplier? 95, right? It's going to be 95% or 0.95. But sometimes, and in one of those problems, and I don't remember which one it was, we found a number, and you needed to be able to look at that number, and I think it was one that we did yesterday, it was 97 something, or maybe it was 9, I think it was 9, something like that. And you need to look at that number and say, well, gee, that's almost 100%. And at that point, you needed to think, and it was decreasing, so you needed to think, because the question was, what was the rate of decline for a population problem? Okay?
Yeah, because like with the one with the half-life and everything, like I didn't know if you would use 0.5 as the multiplier.
It is 0.5 because it is decreasing by 50%, half of a life.
But so then you plug in the 200 grams for the initial amount, so A equals 200 times 0.5 to the, and it was 75.5 years.
Yeah?
All right, but then what does that gives you when you get that?
The formula is A is equal to PBT.
Right.
P is your initial amount,
Which was 200.
okay, which is 200, and then your A is what you will get at the end. If it's increasing, what it is increased to, or if it's decreasing, what you have after.
But what I just got confused on is when you do 200 there, you do 0.5 for the B, and you do 75.5 years for the T, you don't get 0.997.
I don't think.
No, you're going to get this. It's in relationship to this. So which problem are you talking about?
I was talking about the one that we did yesterday in class. I didn't figure out what that applies to all of them. But I think I get what you mean.
Could you just give me do you remember which problem it was?
It was.
Yeah, it was the Explorer.
628.
Oh, the Explorer.
We did it, or we started it yesterday.
Okay.
Well, how did you find out the T?
628. Sometimes we're going to use graph it. We haven't done much on the exponents, finding an exponent. Okay, so at this time, T is your time. We talked about looking at a graph, and you can predict where your graph will be at a certain time. That's what we're going to be using logarithms for. We're going to use logarithms to help us solve variables that are exponents. Okay? Emily? Yes.
I think I get it.
Okay. So in number 1, let me see, am I on the Explorer? Okay. Is this where we were at?
Yeah.
Okay. The question yesterday was, I think this was a lifespan of 75.5 years, and what is the time? If this is the decrease, it's not even one lifetime, right? Because what is the half-life? 24,400. So it's not one half-life. It is a very small percent or fraction.
Yeah.
So that's how I got 75.5 out of all this number, and it's a teeny number.
That's what confused me, was I thought you were doing just the time.
Yeah,
so I did
that's what I thought.
75.5
And that's why I messed
as
it
the
up.
exponent.
Okay.
The number of times the B is being
mathematicians, and this is going to be critical. Remember, PEMDAS, parentheses, exponents, and we're going to spend some time today. I'm going to make sure that you use your calculator correctly. Laura's not here, and know that it's all about those parentheses, and we're going to spend time making sure that you enter in your data correctly. Okay? Are we good to go? All right.
Wait, so why'd you divide 75.5 instead of 24, 400?
How many half-lives?
Because this is the half-life. It takes this much time for this to reduce in half.
Right.
Okay, but the problem happened to be in the lifespan of a human being, which is approximately 75.5 years.
I
So
got
you were
it, yeah.
given this information.
One person's like.
So that's like how much,
So
that's like what percent of that
that
person?
in your lifetime, if you get to be a nice old man, wouldn't you like to meet Michael at 75? I'd love to see him out there in the porch with his grandkids or something. Huh? Is that a scary thought? With all of you with grandchildren, oh, hi, Mrs. What? Oh, I'll be long gone by the time you're grandparents, but, okay. The point that I'm making, Kayla, is, Mike, is that a scary thought, thinking of yourself as grandparents? It is.
I already have 2
It's
kids.
gonna be old. Scary thought for me, and I'm not one yet. I'm a lot closer than you are. Okay. So, is this a fraction of a half-life?
Yep.
And that's how we ended up with this, what it would be over time.
Yeah.
Because I tried redoing it, and that's, if I'd have done that, I would have had it.
Okay. So, and then, I mean, look at how much is left in 75 and a half years of the original 200 grams. Okay, so that's why you as mathematicians, as scientists, as engineers, as the future, it's your job to think about renewable energy. Maybe going nuclear isn't the wave of the future. Told you, my daughter just graduated. There are nuclear engineers, and I said to her, I asked her, I said, so how does your classmates feel about nuclear energy? And they said, nuclear energy is here to stay because we cannot create the energy that we need at this time through wind power or solar power. Wind power and solar power, and I don't remember the fraction that she told me, but it is not enough. So if we're talking about that nuclear power is here to stay, what do we need to make sure? Well, we can create a lot of nuclear power with it.
Take care of the
Except Germany.
That we take care of the waste, number one.
35.
How about the plants? That the plants are safe. I mean, look at what happened in Japan. You know, they built it to withstand an earthquake, but water, they didn't anticipate. Think about that, human error in terms of design flaw. So, I mean, you know, those are things that you all need to be aware of. Yes?
No, I was just going to say, I heard that there's 2 countries, I forget, Germany's
Germany.
one of them, I forget what the other one is. They're planning to phase out nuclear energy by 2030 something.
Well, but you know
I don't know
what?
how that's going to work, but Germany's like mostly green power anyway.
But no, what they're going to do is they're going to buy it from somebody else. So they're depending on somebody else having, you know, not in my backyard. They don't want it, but Czechoslovakia, they're going to use it. So it's true. Okay, so we're ready to roll because today's lesson is really related. And before I begin, perhaps the juniors in the class would like to share what they know about E. Who is E? What is E? E-I-E-I-O.
Oh, God.
E-I-E-I-O. Yeah, there you go. Another song for your Michael. E-I-E-I-O. What?
We don't really know what E is, the way that
Shh, let's listen, okay?
it's like, we don't really use E, but for example, like if we use it,
You know what, Zach and Eli? It would behoove you to listen to
it's
this.
like we use it, we have this equation, that's, ln and then times nt over no is equal to negative kt. And when it's like nt over no, if you're solving for something that's in the ln, then you have
And
to
ln
do
stands for what?
natural log.
Good girl.
Then you have to do e to the negative kt power.
Okay, good. So we're going to be using natural logs, logarithms, and E is one of the most important numbers when it comes to logarithms, yes.
I have a question. E shows up, and I don't know if this is the same E or not on the
No,
calculator. to
different E.
multiply.
That
Okay,
E
that's
stands for
it.
exponent.
Okay, that makes more
I like
sense.
that.
Okay.
What is a logarithm exactly?
We're not there yet, that's gonna be tomorrow, okay? So, let me tell you what I'm gonna, about E. So,